We are looking into retrosynthetic analysis and applications. In this topic, what we are supposed to learn is the strategy of making molecules by adopting an approach of first breaking down that molecule into simple units and then again reacting those units together to make the original molecule. So this kind of approach is called as retrosynthetic analysis. Retro means going back and then you are synthesizing that molecule by going back and finding simpler molecules. So once you are able to understand this chapter, what you should be able to do is you should be able to suggest all the steps or reactions to make a given target molecule. We will look into some fundamental ideas of retrosynthesis with the help of some definitions. The first definition is target molecule. Any molecule which you want to synthesize is our target molecule. Here I am giving an example of alpha beta unsaturated aldehyde, which is crotonaldehyde. And we are supposed to think about simpler steps of making this particular compound. And we will think about the ideas of making this compound that will be called as retrosynthesis. So another definition for us is retrosynthetic analysis. It is the process of breaking down a target molecule into simple and available starting material by using two strategies. The first one is disconnection and the second one is functional group interconversion. And these strategies are used as per the structure of the molecule. For example, in this particular molecule, which is on the screen, that is crotonaldehyde, we will be using both the strategies and we will try to find out a simpler solution of making the structure. So let us go to another definition, that is functional group interconversion and disconnection. Functional group interconversion, it is the process of converting one functional group into another. I will give an example here. We have an alkene in this molecule and a carbonyl group, and what we will do is convert this alkene into an alcohol through functional group interconversion. So what I have done is added one OH group on the beta carbon and added a hydrogen on the alpha carbon. So that is how you have converted this alkene into an alcohol. That is, one functional group has been converted into another functional group. This is called as functional group interconversion. We will look into the another definition, disconnection. It is the imaginary breaking of a chemical bond to recognize possible starting materials. This is the molecule which we have got after using functional group interconversion strategy. Now on this molecule I will apply the strategy of disconnection. So we will break the OH bond towards carbon, and when you make one, you break one. So this is the arrow which is going towards carbon, and as a result of this disconnection we are going to get two fragments. The first fragment which we have got is an aldehyde molecule, acetaldehyde, and the other fragment is a carbanion, carbon with a minus charge. These two fragments which we have got are called as synthones. So we will look into another definition, which is synthone. It is an idealized fragment, usually a cation or an anion, resulting from the disconnection. It may or may not be an intermediate in the corresponding reaction. So when we were applying this approach of disconnection on this molecule, we got two fragments, and these two fragments are now called as synthones. Reagent is a stable compound which is synthetically equivalent to a synthone. For example, if you remember, the carbanion which we got from the disconnection approach in the previous slide, this carbanion is unstable, being an ion, and its synthetic equivalent will be an aldehyde, which is similar to this carbanion except for an addition of a proton. So what we do is we write the synthetic equivalent in this form, that we write the synthone, and we write its stable form by showing equivalence symbol. So basically what we do in retrosynthetic analysis is recognize the function group in the target molecule. Then if needed, then we do the functional group interconversion, or we use disconnections. Both the strategies can be used as per the requirements, and then we get synthetic equivalent or stable reagent from the synthones, and once we get them, we can complete the synthesis. So in the coming discussions now, we will solve some examples and try to understand the complete retrosynthesis. That is, we go back to get the starting material, and then we use the starting material again to find the to make the target molecule. So we have a question here. We will solve this complete question by using retrosynthetic analysis. We are given crotonaldehyde, and we are supposed to complete the retrosynthesis of crotonaldehyde. So this is the crotonaldehyde molecule. As you can see that this is an alpha beta unsaturated aldehyde. This is the functional group, and after the functional group, the carbon which is next to the functional group is alpha carbon, and next to alpha carbon we have a beta carbon. So when we get this kind of unsaturated aldehyde or ketone, which is usually called as alpha beta unsaturated aldehyde, alpha beta unsaturated ketone, what we do is the first strategy we apply is functional group interconversion. And what we do is we convert this alkene into an alcohol by adding water. So we are converting this alkene into alcohol, one functional group into another functional group by adding water. But we take care that when we are using this strategy of converting the functional group into alcohol, we add OH on beta carbon, and what you are going to get will be an alcohol in which beta carbon has OH and alpha carbon gets hydrogen. This is how we do the functional group interconversion. So this strategy you should use for each and every alpha beta unsaturated aldehyde or alpha beta unsaturated ketone. So you have done the FGI. Now we will use the disconnection approach. And what you do in disconnection, you start from alcohol group, that you break the bond of alcohol, make on towards the carbon. So you are making a double bond with this carbon, and arrow goes towards the alpha carbon. So once you follow these two arrows, this is the disconnection approach. We are breaking the bonds. So what you will be getting is an aldehyde, acetaldehyde, right? This is one of the synthones we are getting, and the other synthone will be a carbanion. So out of these two synthone, one is stable synthone, the other one is unstable. So this unstable synthone, we should find out the synthetic equivalent, and that synthetic equivalent will be nothing but an aldehyde again, which we will be getting by addition of a proton here. So on this CH2 we are adding a hydrogen, right? So we get again acetaldehyde. So here what you can see in totality is that we started from an alpha beta unsaturated system, And at the end, what we are getting is two small acetaldehyde structures by using FGI and this connection. So this is the retrosynthetic analysis. Remember that the strategy which we used is we add water molecule across the double bond in alpha beta unsaturated aldehyde or ketone, and then you must take care that OH needs to be added always on beta carbon. So here we have this OH, and then you use the disconnection approach. You get two fragments, and then you convert the unstable fragment into a stable fragment by giving it H plus. So now we have got these two starting materials. This we can use to complete our synthesis. So when we react these two molecules together, we'll be getting our target molecule. So let us see how we are going to do that. We have our synthone acetaldehyde which we got from retroanalysis. This acetaldehyde will be converted into carbanion by using NaOH base. OH minus is taking out this proton. Bond is breaking towards carbon. It is receiving the electron, so it becomes negatively charged. Now this carbanion which we have got will attack on another acetaldehyde molecule. In this acetaldehyde molecule, we have electron deficient carbon because of oxygen, and you will attack and make a bond with this carbon. When you make one, you break one. So we are getting a structure where these two carbon units are joined together to give you a 4 carbon molecule with a minus charge. And because water is available in the system, so O minus is taking the proton, and what we get is OH from O minus. Now on heating, this molecule is losing water, so dehydration takes place. The mechanism which is followed here is conjugate base elimination. That is, first carbanion is generated on this CH2, that is alpha carbon, and then C minus is pushing out OH minus. So we are not going into that part. We just remove water molecule from this system and we make the final product. This is our target molecule. So we were asked to synthesize this molecule by using retrosynthetic analysis. So what we did is first we used FGI and then interconversion FGI and then disconnection approach, and finally we synthesized this molecule. Previous example was alpha beta unsaturated aldehyde. Now we have one more example. This example is of a ketone which is alpha beta unsaturated. So this is alpha bond and this is beta bond. There is a double bond between them. A similar strategy we can use. We can convert this alkene into an alcohol by using FGI. We take care that when we are adding water, beta carbon is getting OH and alpha carbon is getting hydrogen. So this is the FGI. And then we are using disconnection approach where we are breaking the bond between oxygen and hydrogen. And when you make one, you break one. So what you are getting is a C double bond O at beta carbon and a minus charge on alpha carbon after the disconnection. And this particular molecule is an ion, so we are converting it into a stable form by adding one hydrogen. So we are finally getting CH3 at alpha position. So this is the starting compound which we have got after using this retro approach. And now what we will do is we will complete the synthesis of this target molecule, that is alpha beta unsaturated ketone, from this starting material. So let us go for the synthesis now. So we start with our compound. CH3 is now written as CH2 and H because I want to remove a proton from this alpha carbon. So base is there, which will take out the proton, and we are getting the carbanion with carbon with a minus charge at alpha position. And this will attack on the neighboring carbon again because this carbon is electron deficient, as we know. And when you make one, you break one. So a bond is breaking towards oxygen. What we are getting is an addition product where oxygen is with a minus charge. We have water in the system, so O minus is taking the proton from water and it is becoming OH. And on heating, dehydration takes place. OH is lost from beta position and a hydrogen is lost from alpha position. And what we are getting is the formation of double bond between alpha and beta. So this is our target molecule which we have got by using the same strategy. We will see one or more two examples. Here we have another molecule which is, if you see, alpha beta unsaturated ketone. At alpha carbon and beta carbon there is a double bond. What you will do is use the same strategy of converting this alkene into alcohol by functional group interconversion. You add water. Take care that you are adding water in such a way that alpha carbon gets H and beta carbon gets OH. So always add OH on the beta carbon and then use disconnection. When you make one, you break one. So what you have got is this particular molecule with a minus charge at alpha position. You give hydrogen, you give a proton to that carbanion, and what you are getting is our starting compound. So this is our starting compound, which we can use to complete the target molecule. All these examples are basically examples of aldol type condensation, right? So we will go for the actual synthesis of the target molecule. So we have our starting compound. We use base to remove the proton and generate a carbanion. Once the carbanion is formed, this carbanion will attack within the molecule. So intramolecular aldol is taking place. Minus will attack on this carbon, which is electron deficient. When you make one, you break one. You are getting the ring formation, right? And oxygen will get the minus charge. Then this negative ion will take proton from water. It will become an alcohol, and this alcohol has now provision for loss of water. So we have alpha carbon and beta carbon. OH and H is lost. So this OH is lost and this H is lost. And what we are getting is the formation of a double bond between alpha and beta carbons. So this is how you can solve all the examples of alpha beta unsaturated aldehydes or alpha beta unsaturated ketones. Some more examples are cited here. You are advised to solve all these four molecules on your own. Use a proper strategy. All these are alpha beta unsaturated system. So use FGI to make alcohol. Use disconnection to get the fragments and again reconstruct the molecule. When we talk about higher alcohols in retrosynthetic analysis, then what we do is we are using a different strategy uh, of getting these alcohols from Grignard reagent. So here what we have is propane 1-ol, and this alcohol or any other higher alcohol can be synthesized by using the strategy which I am going to show you now. So what we do is we are converting this primary alcohol group by shifting the bond, disconnecting it, and we are getting formation of a carbanion, and we are getting formation of double bond between carbon and oxygen, so we are getting an aldehyde here. So what is happening here is that this single bond is receiving the electrons. So this single bond is now a double bond between carbon and oxygen. Electrons are going towards this carbon. This is CH2. So CH2 is receiving the electron. It is becoming carbanium. Now this is a stable compound, of course, but this carbanium is not stable. So this is a synthone which is unstable. This needs to be converted into a stable molecule. And what we are using is the Grignard reagent in its place because we need a minus charge on carbon. So in Grignard, we know that carbon which is connected to magnesium is electron rich in nature. So when we converted this synthone into a reagent, we did not add directly a proton. We did not convert it into ethane. That would be a wrong strategy because then in ethane there will be no carbon with electron richness. We need a carbon which is electron rich. So I am not using this strategy of directly putting a proton on this carbanium, and I cannot convert it into ethane because I need a carbon which is electron deficient. So I am converting into another equivalent molecule which is giving a minus charge also on this carbon. So this is how we write the reagent or synthetic equivalent of the synthone. Now we have got these two starting compounds, and what we can do is use these two starting compounds to complete the synthesis. Let us see how we can do that. So methanol we have and Grignard reagent we have. We know that this carbon is electron deficient because of oxygen, and this carbon is electron rich because it is the Grignard reagent. Magnesium is a donor, and carbon having more electronegativity gets the minus charge, partial minus charge. Now what we will do is charge distribution. So minus will attack on plus. When you make one, you break one. What you have is CH3, CH2 attacking on the carbon of aldehyde. So this is the new bond which is formed, and oxygen is receiving the electron, and it is also getting MgBr from the Grignard reagent. This adduct is unstable, which can be decomposed by using water and HCl always. So when you are putting water and HCl, this OMGBr becomes OH, and we are getting our target molecule. So important parts to remember is that electron rich carbon of Grignard reagent is attacking on electron deficient carbon of aldehyde. That is one part. In Grignard reactions, we always use dry ether. The addition product is kept in the square bracket, and it can be decomposed with the help of water and HCl, and then OMGBr always becomes OH. So this is how you can prepare higher alcohols by using Grignard reagent and a suitable aldehyde or ketone. So we have to see another example here. This is the alcohol which is secondary, and the name for this alcohol is butane 2-ol, right? And what we will do is use the disconnection approach, which is also kind of converting this alcoholic function group into carbonyl group. So when you make one, you break one. Follow the arrows, and what you will do is you will write CH3, CH2 repeated here. What you see here is that this bond is coming on to oxygen. So this single bond between carbon and oxygen is converted into a double bond, right? Plus this bond is going towards methyl, so this will become methyl carbanium. So these are the two synthones we have got. One is a stable one, propanol. The other one is an ion with a minus charge. So when we want to look towards its synthetic equivalent, what we do? We make it into a Grignard equivalent. So this is the synthetic equivalent of CH3 minus CH3 MgBr, and this CH3 MgBr will have partial minus charge. Fine. So we have got our starting compounds. What we'll do is complete the synthesis. So we have these two starting compounds. One is propanol and one is methyl magnesium bromide. So we react them together. The conditions are dry ethers. We know the electron distribution. This carbon is electron deficient. This carbon is electron rich. When you make one, you break one. So dry ether. And what you have got is an addition product where O is opening up its double bond and it becomes OMGBr. CH3 has made the bond with this carbon. So we have CH3 connected to this carbon. We put the square bracket, work up the reaction with hydrogen chloride and water, and OMG becomes OH. So this is the target molecule which we have got here as the first product. So this is a secondary alcohol which we have used the same strategy. We can have some more examples. This is the benzyl alcohol. Use the same strategy and you can get the one Grignard reagent and one aldehyde. Here it is a tertiary alcohol. So what you will be getting um, is an alcohol which will be, this alcohol is tertiary. So what you will be getting will be a ketone and Grignard reagent. So you can try these four molecules for practice and try to solve. First do the retro analysis and then write the complete synthesis. So it has two parts. First do retro to get the starting materials, then use the starting material to make the final compound again. So esters are another example of molecule which are given to solve. Here ester is supposed to be broken down by disconnection, and what you need to do is break the bond between carbonyl and oxygen, and then you will be getting two parts. So we are using disconnection approach. So we are getting these two parts. Now when we are using disconnection approach, we need to put the charges on the fragments because we are breaking the bonds, right? So this carbon being connected to oxygen, definitely oxygen will be withdrawing electron density from carbon. So this carbon is given positive charge. Oxygen is known to be an electronegative atom, so the minus charge can be conveniently given to this oxygen. So we put the charges in this way, C plus and O minus. So these are the synthones. Both of them are ions. Both of them are unstable species, and we need to convert them into their synthetic equivalent, which are stable also. So what we will do is, for this carbonyl with a plus charge, we will convert it into a corresponding chloride here. So this is the synthetic equivalent or reagent obtained from the synthone. So this synthone is converted into its reagent, and this synthone will be given a proton. So O minus take up that proton, and then it will become an alcohol. Now this particular synthone, with this particular synthetic reagent or synthetic equivalent which we have got is an acid chloride. So we can look towards making a more stable equivalent. So in place of acid chloride, we can think of getting an acid through the LGI. So functional group interconversion, this COCl group is now converted into COOH. So now we have got our two starting compounds. One is benzoic acid and the other one is benzyl alcohol. So we can use these starting compounds and complete the synthesis of this particular ester, which is benzyl benzoate. So let us complete the synthesis now. We have benzoic acid. We convert it into corresponding chloride by using SOCl2. So COOH, OH is replaced by Cl by using this particular reagent, thionyl chloride. We have this benzoyl chloride now, which will be reacted with benzyl alcohol. If you see the charge distribution, oxygen lone pair can attack on this particular carbon, which is electron deficient. So delta plus charge on this carbon. My lone pair of oxygen is attacking. When you make one, you break one, and we complete the reaction by losing HCl. So this is how you can make the esters. So strategy here used is the breaking of bond between carbonyl and oxygen to get the fragments, and then those fragments are converted into simpler reagents which we use to make the ester. Another example here is given as methyl propanoate. So what you will do is again use the disconnection approach, and you know that you have to break the bond between C double bond O and O. So you break the bonds, you get two parts. These fragments are given the charges, which are very logical. Oxygen is more electronegative, so it is given the minus charge. Carbon is given the plus charge. Then these two synthones which we have got are converted into corresponding reagents. So here is added to get acid chloride, and here H is added to get methanol. And then this particular acid chloride can be further converted into corresponding acid by using functional group interconversion. So now again we have these two starting compounds. One is propanoic acid, the other one is methanol. What we will do, we will convert this propanoic acid into into acid chloride with the help of thionyl chloride SOCl2. What we are going to get is replacement of OH by Cl. So this is our acid chloride. Acid chloride is now reacted with methanol. Methanol oxygen has lone pair, and it will attack on this carbon which is electron deficient. So when you make one, you break one, and what you have got is this particular ester again. Aldehydes and ketones, when we are getting such aldehydes and ketones, they can be prepared by this particular retrosynthetic strategy. What we are supposed to do is first carry out the functional group interconversion, where we convert this carbonyl functionality into alcohol functionality by addition of hydrogens. So what we are getting is a hydrogen on oxygen and another hydrogen on carbon. So we converted this C double bond O into alcohol. That is functional group interconversion. Now we do this connection. So during this connection, what we do is break the OH bond and give it towards the carbon. So we are in the process of making a double bond between carbon and oxygen. And when you make one, you break one. So you break the carbon towards, break the bond towards the alpha carbon. So what we have here is two parts. One part is a formaldehyde, and the other part is a cyclopentyl carbanion. This cyclopentyl carbanion is of course unstable, so we will convert this into a stable reagent, and that will be the Grignard reagent. So now we have got these starting materials. One is cyclopentyl magnesium bromide and one is methanol, and by using these two starting compounds we are supposed to make this cyclopentyl carbaldehyde. So let us go for the synthesis now. We have done the retro part. Retro analysis has given us two starting compounds. So we have this Grignard reagent, cyclopentyl magnesium bromide and formaldehyde. Charge distribution wise, if you see, the carbon is electron deficient and this carbon is electron rich. You will make this carbon to attack on electron deficient carbon. So when you make one, you break one. Dry ether is the condition for this particular reaction again because it involves Grignard reagent. And what we are going to get is additional product where oxygen is now bearing MgBr. This addition product is broken down with the help of water and HCl, and we are getting a primary alcohol. This primary alcohol can be oxidized with the help of PCC, pyridinium chlorochromate, Corey's reagent, and we will get the corresponding final target molecule, cyclopentyl carbaldehyde. So this is how we complete the synthesis. So this type of aldehydes and ketones can be um, easily made with the corresponding Grignard reagents. I can give you another example for practice. What you do is make this particular ketone by using the same strategy. What you will do is first use FGI, make alcohol, do disconnection, get the Grignard and corresponding aldehyde, and then complete the retro. Try your hand on this particular compound and take one more. What you can do is use this particular compound where it is again a ketone. So try to solve these two examples by using the same strategy. Do the retro first and then complete the synthesis. Again, we have here acetophenone molecule. This is an aromatic ketone. One part is aromatic ring. So what we will use is another strategy. We will directly use the disconnection approach. We break the bond between the aromatic ring and carbonyl. Disconnection is giving you two fragments because carbon is connected to oxygen. So this carbon should be getting the positive charge, and aromatic ring will obviously get the minus charge. And these two synthones are basically unstable. So what you will do is make stable reagents from them. So for aromatic ring with minus charge, I give it a hydrogen, a proton, and for this particular acylium ion, we are giving it chlorine. So basically, we get benzene as the reagent, and the other reagent is acid chloride. So basically, we can use the Friedel-Crafts acylation strategy now with these two starting compounds, and we can make our aromatic ketone. So, so now we have our aromatic ring as the starting compound, benzene plus acid chloride, and this is the combination of a Friedel-Crafts reaction. So we are using a suitable Lewis acid, AlCl3, and we know that aromatic ring will attack on this carbon to replace chlorine, and we will be getting acetophenone as the final product. So this is how we are getting our target molecule. Now, uh, for the sake of practice, you can use these examples and try to apply strategies to make corresponding aldehydes or ketones. Here we have an alkyl halide, and what we are going to do in order to make this compound is first FGI. So this alkyl halide is assumed to be formed from corresponding alcohol. So this Br is replaced by OH, and now we are using disconnection approach after FGI. So what we do is that we are using the lone pair of oxygen, and we attack on this neighboring carbon. When you make one, you break one. What you are going to get is aromatic ring with a minus charge and a three-membered cyclic compound where two members are carbon and one is oxygen. Because oxygen has given the electrons to carbon, so this oxygen will have the positive charge. Positive charge of oxygen can be neutralized by breaking the OH bond. So first we will convert this aromatic ring with a minus charge into its stable corresponding reagent. So we are making it MgBr here, and from this particular ion or synthone we are converting to corresponding oxygen by losing the proton and neutralizing the charge on oxygen. So these are the two compounds which we can react to get our target molecule. And this particular oxygen, a three-membered ring, it is also called as a epoxide. It is obtained from alkene, corresponding alkene. So this is our final starting compound. So you need alkene, you can convert it into epoxide. You react that epoxide with Grignard reagent to get the alcohol, and then you replace that OH by Br to get the final product. So this is how you can complete your synthesis. So let us go for the synthesis. We are taking ethene. We are reacting with metachlorobenzoic acid, and this double bond will be now converted into an epoxide by addition of oxygen. Then Grignard reagent is coming into the picture, which will react with our epoxide. If you see the charge distribution, carbon is electron deficient in epoxide, and other carbon in the aromatic ring is electron rich. When you make one, you break one. What you are going to get is the addition product where oxygen is now OMGBr. You decompose this addition product with water and HCl. You get corresponding alcohol, and now this OH can be replaced by Br by using NaBr and H2SO4 combination, and what you will be getting is your final target molecule. The cyclohexene molecule is prepared by a very different strategy of 4 plus 2 cycloaddition. So when we are doing the retrosynthesis, what we are supposed to do is shift the pi bond from this double bond on one side and complete the cycle of when you make one, you break one, and keep doing it till you complete the cycle. Once you have rotated these three arrows, write the product, and what you will find that this single bond is becoming a doubly bonded ethene, and the other part which you are getting is nothing but 1,3-butadiene. So this is how you are getting these two products. And this is a 2-carbon system, this is a 4-carbon system, and when you are doing this cycloaddition reaction, that is 4 plus 2 cycloaddition, you are going to get a 6-membered ring here. This reaction is known as Diels-Alder reaction. So now this is a thermal reaction. So when these two structures are heated together, we will be getting cycloaddition reaction. So this alkene will attack on 1,3-butadiene. When you make one, you break one, and then again this bond will shifting towards ethene. This is how we get the completion of the ring with a double bond. For the sake of practice, what you can do is use three molecules, do the retrosynthesis, and again complete the synthesis. This is a molecule where you see diethyl malonate system. Probably you can identify it here, right? So what we will do is you will use the disconnection approach, and we will break the bond between CH2 and CH. So this particular bond between CH2 and CH will be broken down as a disconnection approach. We are going to get the two fragments, and what I have done is given the electron density towards this CH, so benzyl part will be getting the positive charge, and the other diethyl malonate part will be getting the minus charge. From the benzyl part, we are putting bromine and making the equivalent structure, and from this diethyl malonate part, we are putting a hydrogen, a proton, and we are getting the stable starting compound. So these two structures will be our starting compounds, which can react to give us this particular target molecule. So to start with, what you will do is you will use dithionbenonate, the suitable base, sodium ethoxide, take out the proton, make the carbanion, and this carbanion is now reacted with benzyl bromide, this carbon being electron deficient. O minus, sorry, CH minus will attack on this carbon. When you make one, you break one, and you are getting the final product. This is how we complete the synthesis. Another class of given compound is cyanohydrines. What we do is use the disconnection approach. So this OH bond is broken down and it is being close towards carbon. And when you make one, you break one. So on disconnection, you are getting an aldehyde. This is the newly formed double bond after the disconnection, and the other part is Cn minus ion. So we are getting these two synthone. One is stable. It can be directly taken as the starting compound. This Cn minus is converted into its suitable reagent, that is hydrogen cyanide. So now we have our two starting molecules. We can complete our synthesis by taking these two molecules. Hydrogen cyanide is a weak acid. It gives H plus and Cn minus ion. Cn minus is a nucleophile, and in this molecule carbon is electron deficient. So what will happen is Cn minus will attack on this particular carbon. When you make one, you break one. So we get the final product here. So this is an example of nucleophilic addition reaction. These are the cyanohydrines which can be prepared by aldehydes or ketones, corresponding aldehydes and ketones. So for the sake of practice, you can take up these three examples of cyanohydrines. You can see a cyano group and OH group. So these kind of structures can be having similar strategies for their synthesis, that is disconnection approach, and you can try to complete the synthesis for these three molecules. So that is the end of the chapter retrosynthetic analysis, where we have taken various examples of different molecules from different families. You are supposed to do enough practice so that you can apply the strategies of disconnection and retrosynthesis as per the structure of the molecule, and with some practice only you will be able to decide which strategy is useful for a given structure, whether we are supposed to use FGI first and disconnection later, or disconnection first and FGI later. All the best.